We tend to treat artificial intelligence as a limitless, magical technology, but it is bound by a severe physical constraint. The energy required to run these models is projected to double by 2026. That massive power draw traces all the way back to a hardware blueprint drafted in the 1940s. It is called the von Neumann architecture, and it still runs almost every computer on Earth. The defining feature of this setup is a strict physical division. You have a unit that stores memory on one side and a central processing unit, or CPU, that does the actual math on the other. To execute an AI algorithm, a processor has to continuously shuttle billions of data points back and forth across the channel connecting those two units. This creates a massive traffic jam, known as the von Neumann bottleneck, and pushing data through it burns immense amounts of time and electricity. We are trying to run exponentially growing algorithms on a rigid 80-year-old hardware frame. The physics simply do not scale. The human brain, however, processes complexity and learns in real time through the constant firing of biological neural connections. Yet it performs all that heavy lifting on roughly 20 watts of power. That is less electricity than you need to run a standard household light bulb. Instead of trying to squeeze a few more drops of efficiency out of legacy silicon chips, engineers began looking to this biological structure as a physical blueprint for artificial intelligence. In the 1980s, an engineer named Carver Mead proposed treating a computer chip like a biological substrate. This approach is called neuromorphic computing. To build a neuromorphic chip, you first have to completely abandon the von Neumann model and erase the physical boundary between memory and processing. Instead of separate units, these chips use an artificial synapse called a memristor. A memristor is a unique electronic component that can store data and execute mathematical logic in the exact same physical location. With memory and processing physically co-located, there is no central data highway. The chip never has to shuttle information back and forth. The hardware is no longer a sequential calculator. It is a highly distributed, parallel physical structure, mirroring the synapses in your head. The second major difference is how these chips manage time. Traditional processors run on a continuous synchronous clock, but neuromorphic chips use spiking neural networks. These networks are entirely event-driven. The artificial neurons sit completely idle, drawing absolutely zero power until a specific input threshold is met. When triggered, they react by spiking. A standard CPU ticks relentlessly, drawing electricity every microsecond, whether it is doing useful work or just waiting for data. The spiking network only fires when it has something to say. By engineering hardware with the biological ability to rest, the system turns idleness into an enormous operational advantage. When you scale these microscopic artificial neurons up into massive production units, like Intel's Loihi or IBM's True North chips, the impact on power consumption becomes stark. This chart shows the energy consumption of standard GPUs compared to neuromorphic processors. For certain AI inference tasks, the neuromorphic hardware requires up to 21,000 times less energy than the traditional GPU to complete the exact same workload. That sheer drop in power requirements means complex artificial intelligence is no longer tethered to massive water-cooled server farms in the cloud. We can now deploy what is called edge AI. We can place powerful, adaptive intelligence directly onto small, portable, battery-powered devices. In the biomedical space, researchers are using this hardware to build continuous, real-time EEG wearables. These devices can monitor brain waves and predict epileptic seizures accurately, operating entirely on a milliwatt power budget. In autonomous vehicles, this low-latency processing allows cars to execute split-second collision avoidance locally. The vehicle does not have to wait for data to travel to a remote server and back to make a life-saving decision. Neuromorphic engineering dismantles 80 years of computing logic, moving beyond simple iterative improvements in processor speed. By modeling hardware on human biology, we have moved past simulating intelligence through brute force to building chips that physically function like a brain.